Hey, welcome back to this old basement. What you see here are two drive shafts. This is a project for a friend, so this is no customer work. What he wants me to do is to make a coupler that goes over the Splinedrive and couples those two shafts together. So we will machine one out of 4140 commercial heat treat steel that already has about 1200 Newton per square millimeter of tensile strength, and use the mill to slot the profile of the Splinedrive into it. And how to figure out the profile and grind the tool, etc., that's all in this video. Here you have the Splinedrive in close up, and out of an dowel pin I ground me a 60-degree point. I looked up Splinedrive profiles, and usually they are 60-degree included angles, so I made this pin to check it. As you can see, against the light, I have my desk lamp behind it. This makes pretty good contact. But if you look on the right side, where it contacts the wall of the gear tooth, the side of the gear tooth, you can see that it contacts only in the center and not above or below. That tells me either this is machined not very good, or it's an involute profile, involute gear style profile. I could online not find if these axles have an involute or a straight spline. Couldn't figure it out. Just goes to show there can be more to such a drive than just a straight wall. Just to break it down again. Normal Splinedrive looks like this. And it has like 60-degree included angle, straight sides on the teeth. The involute profile looks more like this. And once again, I'm far from an expert on this. I'm figuring this out as I go. So let's say you have a circle that magically appeared on here, and you take your involute drawing instrument, which is a string with a knot in it, and you poke your pen through the knot, and you get some tension, and when we start to draw, the cord or the string will unwrap, and that will create the involute curve. There you go. That's our involute. That's, by the way, also how gear teeth are designed, like on a spur gear. It starts out almost square, then it goes off into this long curve. This is not a continuous radius. This is like a spline, like a Bezier curve in CAD. And I'm pretty sure that the splines on this are like this. I talked to my friend to make a long story short. We will ignore this and we will just cut a 60-degree profile. As far as I can tell, the 60-degree profile hits on this teeth basically here on center of the teeth. So should be good. If we add a little bit of force and elastic deformation, it will make very good contact. I'm not very worried about that. As I said, we're not going to make a science fair project out of this. But I wanted to get the rough idea how to do this out of the way. Okay, now we have kind of figured out the profile of this spline here. We need to figure out how our tool needs to be shaped. The 60 degrees are obviously, because that's what we checked by with the 60 degree pin. That's, in all honesty, way good enough for this purpose. And now we need the width of the teeth on the tip here. That's the smallest dimension. That's what we're going to grind on the tool. And we can measure that close enough with a pair of calipers. Yeah, it measures 105 millimeters. I will grind it to 1 millimeter just to give a little bit of head clearance. Okay, we're over at the D-bit grinder. I found myself a piece of 8mm high-speed steel, round, holding it in a collet. Everything is set to 0 right now. Up here, the dividing head, this joint and this joint, this is all 0. First, we want to grind the triangular profile of the cutter, preferably on center. So we start by rotating this in -30 degree direction. That's the first side of our triangle. Today I'm using a CBN grinding wheel. This is a C125 grit, reasonably fine, but not so fine it's slow to grind. It's still a relatively aggressive wheel. And right now we're just concerned with removing most of the material. We position our work head in a way we can use it. Always do a little bit of a try run. We need to cut 16 millimeters deep. So we will grind a little bit deeper and go for it. I have my dust extraction here, just to keep the majority of the grinding dust away. Just to show you the progress of my grind, I'm grinding the two flats alternating, always moving it like this, and then 60 degrees over, 60 degrees back. And that way my profile stays on center. That's very useful if your slotting tools are ground to be on center line, because then you can use the spindle of the mill to center on your part and you're good to go without many problems. But we're getting there. Getting relatively hot. It already has a nice golden color, but high-speed steel is not really affected by that. You saw me use this here. This is a dressing stick to clear out the CBN wheel once it gets clogged up like this. That happens when you grind too hard and too aggressive into a CBN wheel. Happens usually only on a manual machine, like a tool and cutter grinder. Surface grinder, not that much of a problem. These are aluminum oxide sticks. They come in different grits. This is a 240 grit, suitable for this grit of CBN wheel. Usually when you buy these, you will find a chart that tell you the grit you need for your wheel you have. You use these on diamond wheels and CBN wheels. And those are not actually for shaping the wheel. Those are only to break down the binder surrounding the CBN or diamond grit that prevents the wheel from cutting freely. So this is only to make the wheel cut nice and aggressive and relatively cool. Okay, now you can see the overall profile I cut. Nice triangular 60-degree shape. Next I will remove quite a bit of material here, so I don't have to grind a frontal relief angle all the way up to there. And I will do the same on the sides too. So basically what I'm going to do is about from here to here, I will grind all this back about 0.2 or 0.3 millimeters. Same on this side and also on the front here. On the front probably even a bit more, it doesn't matter that much. And I do this so I do not have to grind a relief angle over the whole length of the tool and weaken it that way. Relief angle over the whole length usually tends to create a very thin tool back here, and that's bad because it's fragile. So let's go back. And the way we grind this is we'll just move it here, plunge in, do our motion, plunge a little bit deeper, move it until we're satisfied with what we get. Okay, that's our relief grind on the first side. As you can see, nothing spectacular. Now we do the same on this side. There we go. That's our relief grind. Ugh, smoking hot. Now we go for this side. We'll put also quite a bit of relief grind here. Now we have this shape. Already starts to look like a slotting tool. Next we'll grind the side relief. Very little only, but we need it, otherwise the tool tends to rub on this face once the cut gets a little bit deeper. So better put a little bit of relief in there. To grind the relief, we use this joint here. But we can only go up to 0 degrees or 90, depending on which direction you're thinking. And that's a problem. So we pull this pin down here. There's a pin that can be pulled and also locked open, but in this case we only need to pull it. This is, by the way, also the stop for this adjustment here to set your 90. You loosen the small set screw here and then you can rotate the stop. The stop pin is eccentric, and once you get a small wrench on this hex in here, you can adjust your 0. And the way you get your zeros, you clamp a piece of round stock in here, you grind a flat, you mic both ends, and then you adjust your stop pin until the flat is on both ends of your test bar the same width once you have grounded. So that was the 30-second rundown how to adjust your D-pad grinder square. And we will just put about 1.5 to 2 degrees of back rake on this tool. No need for a crazy amount, we're just slotting. Now we turn it back to 90 degrees and we take care of this front edge here. And we grind this until we get our 1 millimeter width of cut. Okay, double checking. Yeah, that's pretty good. That's very close to 1 millimeter. Last step is to grind the front rake. Otherwise this would be a 0 degree tool and the cutting forces would be reasonably high. So let's turn this. Set up for grinding the front rake of the tool. I have it set to 7 degrees down here, so the whole head is tilted back a little bit. And this is oriented so that the cutting edge, the narrow part of our tool, is pointing straight up. And now we will just feed it into the wheel until we clean up all the way to the cutting edge. I'm grinding that way because the grinding wheel cuts into the steel that way, and we don't get a horrendous burr. The drawback on this setup is that it's hard to get the nozzle of the vacuum cleaner in there. Okay, here is the tool fresh off the grinding wheel. We'll take a closer look on the bench in a second. Okay, we're back at the bench. I took the high-speed steel blank, I cut off the back with an angle grinder chamfer, and I put a shaft collar on it, a split ring collar. And this is just to take up the axial forces. I'm holding slotting tools in Morse taper 2 collets, and the axial forces would over time drive the tool deeper and deeper into the collet, and I don't want that. So I put the split ring collar here, and this takes all the axial forces. We have our 60 degree included angle between here and here. This is all relieved, and we have about 1.5 degrees of back taper on these two surfaces, kind of blending into the relieved area here. Here you can see the blend lines a little bit better. Here the relief is a little bit deeper, and I ground farther up the shank, so I have a flat here that I can use to indicate the tool, so it's oriented correctly. About 7 degrees of back taper here, back rake, to make the cutting edge action positive. So last thing to do is to set up a test piece on the mill and cut it to see if all our assumptions that we took, and that was quite a lot of assumptions, if they all match up. And if they don't match up, I will just edit it out. So I have my rotary table on the mill. I'm not using the dividing head because the dividing head in the vertical position is just builds up a lot of unnecessary height. For vertical shaft work, the rotary table is, in my opinion, the preferable tool. So I have the 3-shot centered on the rotary table, and I have the spindle of the mill centered on my test piece. This is just a piece of aluminium board to the correct size. And you might notice I'm using not my usual indicator holder. This is the indicator holder that I'm normally using. But I saw a lot of people use something like these. This is a small Noga arm. This is an articulating arm that has ball joints. And people seem to like these for centering. But I played with it a little bit, and I have to say I don't like it. It has a few degrees of freedom too much. If you start out on a bore you have no idea where you are, and it's very easy to get it so far offset to the side that your measurements get almost meaningless. So I'm not entirely sure if I like this. I'm very sure I will be going back to my own design, or to my own indicator holder. So next we bring this thing in. This is a 3D printed spindle clamp. This large diameter clamps around the quill, and the small diameter clamps around the spindle. Flexure design, 2 screws pushing in. It's not the perfect design. Indicating the tool. It's low on this side and high on this side, so we tweak it a little bit. Okay, that's within almost 10 micron. It's a little bit low here still. Yeah, that's good enough. Now we can clamp the spindle. Okay, I'm basically done with the test piece. I have one more to cut. Then we can do a test fit. As for depth of cut, we start at 0.2 millimeters for the first cut. As we know, first cut is always the deepest. And then I progressively go smaller. The last cuts are about 50 microns. There we go. That's our profile. Let's move the table out and see if we can get the shaft in there. What a wonderful profile. Looks really, really good. The only problem is I'm a little bit too stupid to count to 20, or in this case to 21. The spline profile on the shaft does have 21 teeth, not 20. Helps if you count carefully. So this goes in my in my shelf of shame, and I will cut a new test piece and repeat with 21. I cut a second test piece, this time with 21 teeth, and when I take one of the axles, it fits. It's a tiny bit loose. It has a little bit of rotational play, not much, but the problem is these parts are not tool and die components. The other axle, which has the same profile, is a mad tight fit. I could assemble it by heating this a little bit or pounding it in with a hammer. But this is almost a perfect fit. A little bit looser than this, and I would be happy. The other one is, in my mind, too loose. But we're on the right track. I will slot both sides of the coupler I'm making to match one of the shafts. So it will have a direction that it will be mounted. But I'm fairly happy how this came out. Next, off to the lathe and preparing the blank for the real part. First side board to the ID, chamfered larger than the final diameter of the Splinedrive, so there's a nice lead in. And I undercut the end of the bore with this piece of chunk tool. Made this long time ago for something else. This is a piece of drill rod, and I just silver soldered a DCMT09 carbide insert to the end and kind of grinded it into shape to do an undercut. Works surprisingly well. Let's bore the other side. I recently bought an ISCAR DF multi-purpose tool. These are inserted drills. These can drill into solid stock. Can also do ID boring, facing from the inside out, OD turning behind the center of rotation on the lathe or upside down. And there are also grooving inserts for them to do undercuts. Quite a versatile tool. Very expensive if you buy them new. I bought it on eBay for next to nothing. And I also got the inserts. These are special inserts. XCMT or something like that. Also on eBay. Too expensive to buy new at the moment. But it's a nice, short and very rigid boring tool. If you want to drill into solid with these, you need at least compressed air through the tool or better coolant through the tool. Otherwise the chips pack up in this area here and you don't get rid of them. But for boring, they work quite nice without. Well, at least a serviceable finish. It's really not that great. But due to the fact that the inserts have a relatively large edge radius and corner radius, they're tough. They're really tough. Hence you can use them as a drill. Now we go for the funny tool. And this will be almost impossible to film for me. I touch the tool here on the end of the part, zero out the DRO, go to the inside of the bore, and I just make a little scratch and check my ID. It's 15.5 and my tool is already calibrated to 55. Now I can go down to final depth, 16 millimeters, and move out to 17.2 millimeters on the diameter of the undercut. And yes, this really will make for a great video because you can see a thing. Okay, there we go. And as you see by the chips, the tool cuts really well. And the sturdy construction of the tool allows for nice chatter-free cut. Some people always have problems with undercutting, and I had too. I really had problems with undercutting IDs. But the trick is really go reasonably slow on the RPM, feed the tool so it actually cuts and does not drop, and design your tool to be as rigid as seemingly possible. I cut the spline profile. Took me 2 tries to get a nice fit on the looser of the 2 shafts. And when we go here with the spline profile, it barely goes in, and it will need assembly with a soft-faced hammer. But I talked to my friend, and he told me he can assemble the whole part as once in one piece, so assembly with a hammer is not a problem. But I looked closely onto the spline profile on these shafts, and these are not milled. These are formed without creating a chip. They're either swaged, like in a like a tool for to swage the end of cables, like a crimp-on connector, and then probably the OD was machined. So these teeth are not crazy precise, and for that reason I'm going with the profile on my coupler a little bit on the tight side, and still be able to assemble it compared to making it too loose and rattling it around. When it rattles around during operation, it will wear. It will create contact corrosion. That's the brown, braided and kind of oxidized material that you find on, for example, 40 taper tooling that has run really, really hard in a milling machine for a long time. And then you take the tool out of the spindle and you get this brown debris. That's part of your spindle and your tool holder that's abraded. Google contact corrosion for that matter. In German we call it Passungsrost, like a close fit rust. Okay, here's another view into the profile. You can see the teeth that we cut, and down here, this is the undercut. This is where the tool, once it has cut the actual tooth, or in fact it cuts the tooth gaps, and 2 tooth gaps form a tooth in between. This down here, the undercut, is where the tool drops free of the cut once it leaves the material. And I set my depth stop so it does not bump into the lower wall of the undercut. That would create a lot of wear on the tool. Just a lot of strain and stress that you don't need. So let's get this out here. I'm quite pleased how this came out. This really looks quite nice. Okay, our rotary table has a ratio of 1 to 90, and the number of teeth we want to cut is 21, not 20. So we put this in a fraction, 90 by 21, and there is already a ratio between the index plate we need and the number of holes we have to go. On a 21 hole index plate we would have to go 90 holes. 90 holes, of course, is like that's 4 turns. 4 turns equals 48 holes. 4 times 21 is 84. Then we have 6 holes. That's the difference between the 84 and the 90. Makes sense, huh? We could shorten this fraction. For example, divide it by 3, or shorten it by 3. That would give us 30 divided by, because 90 divided by 3 is 30, and 21 divided by 3 is 7. That would give us 37th. This is purely hypothetical because I don't have a 7-hole index plate, but let's play with this. That would give us 4 turns. 4 times 7 is 28. It's 28 holes. And the rest, the difference between this and this, would be 2 holes. So, but we can't do this because we don't have a 7-hole index plate. But we have 21-hole index plate, this here. So that means we can do it like this. 4 turns and 6 holes. I talked earlier about my theory of this being an involute spline profile. I'm not so sure about that. Might be, but it could also be that these profiles are just super shitty made. As you can see, the turning work on it is quite rough. This is quite rough. This is a bearing seat. This is machined quite nice. But the spline profile here is really gnarly. And it's not milled or hopped because there is no lead out here. If this profile was hopped or milled, we would have a lead out here from the circular cutter. But it ends abrupt in a sharp edge. And my theory is that these get formed some way of swaging or press forming, almost like forging, and then they just turn the OD, because when you press form this, the material would go somewhere. It would go above the OD, then you turn the OD to clean it up, then you have it induction hardened and you're good to go. So that's my theory why these are so nasty and so different, especially. These are very different fit. I guess my theory about the involute contour was wrong, but I will still leave it in the video just so I can show how to draw an involute and my thinking process behind working on something like this. I usually don't work on parts that have that are vehicle part, but these go, as far as I know, in a model, in a large scale truck model. So this is quite a new experience for me. As you can see, the OD isn't even finished on these. This is still mill scale surface. They just finished this section here. And out here they do the same. And here the profile is even worse. This is a coarser spline profile. And this looks really gnarly. But I think that this side is used already. Part is done. I just threw it quickly in the ultrasonic cleaner to get rid of all the cutting oil on it. Polished the outside slightly with some Scotch-Brite. So I hope this was interesting. Goes to show that the milling machine can do more than just milling. I showed slotting now for numerous times, but this time was a good opportunity to show also grinding such a tool on the D-bit grinder. So I hope it was reasonably interesting. Thank you all for watching and see you next time.